Good morning, everybody. Today we're going to be looking at the beginning of Chapter 14, Section 1, Matter and Thermal Energy. So, one of the main ideas of this section is that matter can exist in three states, and that is solid, a liquid, or gas. Yes, a gas. All right, to understand these states, we have to think about the particles that make up these substances. Molecules, atoms, and ions. They all make up matter, whether it's a solid, a liquid, or a gas. Now, the kinetic theory is the main topic of this particular section. And we need to look at what the kinetic theory is. The kinetic theory, which also sometimes you'll hear it called the kinetic molecular theory, but most people just say kinetic theory, is the assumptions that explain. These are some assumptions that explain how the particles in a gas behave. But interestingly enough, solids and liquids, for the most part, obey the assumptions of the kinetic theory as well. So let's talk about them. Oh, and I just realized there's a typo here. That's supposed to say in a gas, not is a gas. Duh. All right. So the first assumption that scientists make about gases in the kinetic theory is that all matter is composed of tiny particles. There we go, tiny particles. These particles are atoms, molecules, which are groups of atoms stuck together, and ions, which are atoms that are missing or have excess electrons. Okay, so all matter is composed of these tiny particles, whether it be a gas, a solid, or a liquid. Now, these particles, and this is the second assumption, these particles are in constant random motion. Constant random motion. Now, you might be thinking, well, Miss Pepitone, we can kind of see that for a gas. Gas molecules are floating around and just moving around, all right? And we can kind of see that with liquids too, because a liquid flows from place to place and all the molecules are moving around within the liquid. But a solid, yes, the particles are actually moving. Now, they're not moving the way liquid and gas particles move. They can't move through the solid and around the other molecules or atoms. What they do is they vibrate in place. Okay? They just vibrate in place. They're always vibrating like this. Okay? Everything vibrates down in its molecules and atoms. Just a moment. Sorry for the interruption. That was an announcement. Okay, now, the third assumption, besides all matter being composed of tiny particles and that they're constant random motion, is that the particles that we're looking at, all the particles, they collide with each other continually. That's not a very good E. They collide with each other, and the walls of any container in which they are held. So they're constantly bumping into each other and the walls of the container they're in. Okay? And as you know, that's true for a gas and a solid. If you have a tank of oxygen, the oxygen atoms inside are continually bumping into each other and into the and colliding with the inside walls of the container. Same for a liquid. If you have a glass of water, the water molecules are constantly bumping into each other and the walls of the container. Now a solid doesn't actually move the way a gas and a liquid does, but remember, those atoms are still vibrating. If the solid completely fills the container, yes, to a certain tiny degree, they can collide with the walls of the container, but mostly they just sit there and vibrate in place. Now, the fourth assumption of the kinetic energy is that the amount of energy that the particles lose from these collisions is negligible. It means it's not enough to make a difference to anything. Negligible. There we go. Negligible. All right, so all these particles are moving. They have energy. That's why they are moving. In order to move, you have to have energy. And this energy, it's actually quite a lot for such small particles, but when they collide each other, the amount of energy that they lose from these collisions is basically negligible. It's not enough to make a difference. So, because all of the particles move, they have what we call a special type of energy called thermal energy. Now, thermal energy is actually made up of two things. It's made up of the kinetic energy, which is energy of motion, because anytime you see K-I-N-E, that's a prefix that means moving or motion. So kinetic energy is energy of motion, but there's also some potential energy involved, stored energy within the atoms, molecules, or ions. Both of these make up thermal energy. All right? Now, how much thermal energy do these particles have? Well, that's where we take temperature measures. But now we have to be careful. Temperature is not a measure of the thermal energy itself, but it is an indicator of how much thermal energy a substance has. Temperature is a measure of how hot or how cold a substance is due to its energy content, but it's not a measure of the energy itself. It simply means that the hotter or greater the temperature of a substance is, the more thermal energy it contains. So, a freshly brewed pot of coffee is going to have much more thermal energy than, say, cold tap water in the glass. All right? There's more temperature for the hot coffee than there is for the cold tap water. So it has more thermal energy and the cold tap water has less. But remember, temperature is not a measure of the energy itself. We can't measure energy directly. There's no such thing as an energiometer, okay? Temperature simply tells us how hot or cold the substance is, and that is an indicator of whether an object has more thermal energy or less thermal energy than another one. Now, let's talk about changes in states of matter. Can matter in a particular state change state? Certainly, under the appropriate conditions. So let's look and see what some of these conditions are. We're going to talk first about melting and freezing. When an object's temperature reaches the melting point between a solid and a liquid, a solid can become a liquid at the melting point. Now, do all substances have the same melting point? No, they most certainly do not. Different substances have different melting points. And again, it depends on how their atoms and molecules are put together as to whether and what types of atoms they are as to what the melting point is going to be. look at this example. If you take an ice cube out of the freezer and set it in a bowl, as the temperature of the surface molecules of the ice water increases, remember, more temperature, more thermal energy, more kinetic energy. The surface molecules will begin to slide against the colder ones beneath, and they'll slide to the bottom of the bowl as liquid water. Now, this continues with the surface molecules until the whole cube has become liquid. So the ones underneath get exposed, they warm up, they slide against the ones underneath, down into the bowl and become liquid water. Okay? So, at the melting point, the bonds which hold the molecules together as a solid break down, and the molecules or atoms can slide and move as a liquid. Now, the interesting thing is, while the water is melting, its temperature doesn't change. For example, if you put the ice cube in a pot on the stove and you turn the stove on low, the temperature of the ice will increase to the melting point, at which point the liquid molecules on the surface slide off and the next ones start warming up underneath. But the temperature of the ice won't change until all of the molecules have become liquid. Then the temperature can change. Now, what does this mean? This means that the heat energy from the pot, as it's absorbed by the ice, the heat energy is going into breaking the bonds that hold the molecules together. We call this heat of fusion. So the heat from the stove transfers through the pot to the ice, and at the melting point, the heat that's absorbed does not go into increasing the temperature. It goes into melting the molecules. It breaks the bonds between the solid molecules and makes them liquid. Okay, they can slide each other. So the temperature is not going to change while it's melting. The temperature will only change once all the molecules are no longer bonded and they've become a liquid. Then the temperature can change. This is called heat of fusion, the energy needed for all the molecules in a solid to warm up enough to change to a liquid at the melting point. Or, if you go the other way, the heat of fusion is where all the molecules in a liquid lose their energy to become a solid. It works both ways, because freezing is the reverse of melting. So if you have a liquid that gets colder and colder, when it reaches the melting point, then all the liquid molecules will bond together and become solid again. In this case, since we're talking about water, they become ice. So heat of fusion goes into either separating the molecules from a solid or combining the molecules, if they're a liquid, back into a solid, which we call freezing. Heat of fusion. It either melts the solid into a liquid or combines the liquid into a solid, okay? Now let's talk about what happens if you go from a liquid to a gas or a gas to a liquid. All right, if you go from a liquid to a gas, we call it vaporization. If you go from a gas to a liquid, we call it condensation. Let's take a look at that. And I'm going to switch to the next page. All right, now when a liquid gains enough thermal energy or gets hot enough that the molecules on the surface of the liquid actually will begin to have enough kinetic energy to escape the attraction of the other molecules and leave the surface. This is called evaporation. It happens at the surface of the liquid, just like melting acts at the surface of a solid. So as the molecules become warmer and warmer, they can actually gain enough thermal energy in the form of kinetic to leave the surface and become a gas. Okay, now this is why a glass, if you sit a glass on your countertop and leave it there for a few days, you go back in, you'll notice there's less and less liquid in the water every day. That's because the surface molecules, as they warm up, they can leave the surface and become a gas or water vapor into the air, and we call that evaporation. Now, sometimes we can increase the temperature of a liquid to the boiling point. Now, the boiling point is interesting because this is the temperature at which the pressure of the vapor in a liquid, you've got vapor bubbles, you've got them forming inside the liquid and they rise to the surface. But the pressure of the vapor in the liquid is equal to the external pressure acting on the surface. In other words, the air pressure pushing down on the surface of the liquid prevents the molecules from escaping as a gas. Now, this external pressure pushes down on the surface and keeps them from escaping. That's the boiling point. And different substances have different boiling points. For water, it's 100 degrees Celsius or 212 Fahrenheit. Now, what if, however, you've got a substance whose, let's say a gas that's losing thermal energy, it cools down. When it cools down, the molecules compact together and will become a liquid, like fog. Fog forms on the surface of your windows of your car and on the surface of the ground. It forms molecules that become dew. So that's called condensation. When a gas molecules bond together and become a liquid. So evaporation, you go from liquid to gas. Condensation, you go from gas to liquid. Now, either way, whether you bring it to the boiling point and evaporate it past the boiling point or you condensate it, the temperature while the molecules are changing state does not change. Instead, the energy, which we call heat of vaporization, goes into changing the state of the molecules. Sort of like heat of fusion, simply changes the molecules from a solid to a liquid or a liquid to a solid. Heat of vaporization changes the state of the molecules from gas to liquid or liquid to gas. It doesn't change the temperature of the sample. It goes into breaking the bonds or combining the atoms with bonds, okay? Heat of vaporization, and it doesn't change the temperature, which is interesting. Now, heat of vaporization, like heat of fusion, works both ways. Condensation is basically the reverse of vaporization or evaporation, and therefore, heat of vaporization can cause gases to become liquids or liquids to become gases. Now, and interesting, and not all substances can do this, but believe it or not, there are some substances that can go directly from a solid to a gas without even going through the liquid phase. These substances are doing what's called sublimating. Sublimation is simply the process of a solid changing directly to a gas without first going through a liquid state. Not all substances can do this, but a classic example is frozen carbon dioxide, which we call dry ice. If you've ever seen dry ice, you can sit it on a surface and vapor starts coming off of it. It's going directly from solid to gas. Now, you've seen dry ice used before. It's used very commonly for special effects, like especially at this time of year at Halloween, people will put a chunk of dry ice in a cauldron in their front yard for a scary, witch cauldron stirring scene, but the cauldron appears to be smoking and overflowing. It's really just the dry ice that is sublimating. It's turning from a solid directly into a gas. Now, how can we visualize graphically the heating and cooling processes that substances go through when they freeze, melt, condensate, or evaporate? Well, we use a graph called a heating curve. A heating curve to see what happens. So I have here a picture of a heating curve, and I'm going to focus in on it a little bit, and we're going to take a look at this and look at what's happening in each phase of the heating curve. So notice, it says that the graph above is the heating curve for exactly 1 kilogram of water. Now, the water is starting out at negative 20 degrees Celsius. That means it's not liquid water right now, it's ice, because 0 degrees Celsius is the melting point. So at negative 20, it's got to be ice. So for section A, what we see happening is the ice is increasing temperature from negative 20 to the melting point. So we're going to write that down. The ice is increasing temperature. That means it's absorbing energy from negative 20 degrees Celsius to 0 degrees Celsius, the melting point. Okay? So we've added enough heat into our ice to change its temperature by 20 degrees. Now look at the next section, section B. Over a period of time, 1, 2, 3 square, well, a little more than 3 squares, about 3.5 squares of time, however they're measuring the time, you've got the temperature staying the same. What's going on here? Because then you go from ice to now above 0 degrees, it has to be liquid. Well, right here is where we have energy being absorbed as heat of fusion. So the energy that's being absorbed now by the ice is not going into increasing the temperature, it's going into changing the state. Okay, so heat of fusion on section B is changing the state from solid to liquid. That's what heat of fusion does. It changes the state from solid to liquid. While that's going on, the temperature doesn't change. The absorbed heat is simply causing the atoms and molecules to warm up and break the bonds and slide against each other as a liquid. Okay? Now, right here is where we see a change. Okay? We have absorbed all the heat of fusion. Now all the molecules are a liquid at the freezing point. Or, sorry, not, well, it is the freezing point if you go the other way, but it's the melting point this way. So, all of the molecules have melted and they're now a liquid at 0 degrees Celsius. Now we're going to take those molecules and heat them up to, the boiling point. We're going to heat those molecules up to the boiling point. So here we have liquid water. Okay, right here it was a solid. Then this absorbed energy melted it from solid to liquid. Now we're increasing the temperature of the liquid. So let's write that down. All right, so the liquid water increases temperature from 0 degrees Celsius to 100 degrees Celsius, which, if you'll remember, is the boiling point of water. Now this is where we can evaporate the water. All right, so let's look at the next section, section D. All right, and I'm going to have to get the last page here and put it up right here where we can see it. Well, maybe in a moment. Let's look at the graph first. Okay, so here we have the liquid water. Now we're at the boiling point at 100 degrees Celsius. Now, because the water is boiling, now we can use heat of vaporization. Heat of there it is, vaporization. There we go, heat of vaporization. Got to spell it right, don't we? Okay. During this time period, the heat that is absorbed by the liquid water does not go into increasing its temperature beyond 100 degrees. No. It goes into vaporizing the molecules or evaporating them, breaking the liquid bonds and creating gas. The surface molecules can escape as gas now. So, on section D, let's write this down. Heat of vaporization goes into changing the state of the liquid into a gas or water vapor. All right, now once all of the molecules have become water vapor, then the absorbed heat is no longer heat of vaporization because all the molecules are now gas molecules. They're water vapor. So, section E, let's look at it. From here to here, all we're doing is changing the liquid to a gas. From this point now, we have a gas, and any heat absorbed now simply increases the temperature of the gas. So here on section E, absorbed heat increases the temperature of the gas. Okay? Absorbed heat increases the temperature of the gas. All right? And that's a heating curve. It shows exactly what's going on at the different temperatures. We have a solid whose temperature is increasing. Here, it's not increasing temperature, so any absorbed energy is going to changing from solid to liquid. Once it's all liquid, then we can increase the temperature of the liquid by absorbing more heat until we reach the boiling point. At this point, absorbed heat does not increase the temperature, it changes from a liquid to a gas. Takes a lot longer, doesn't it, than it did here. So, for 1 kilogram of water, it's going to take longer to make it into a gas, so we need more heat. Then, once it's all a gas, any absorbed heat will increase the temperature of the gas. Okay? So that's how we show visually what's happening with our changes of state. Okay. Now, are there any other states of matter? We've said there are solids, liquids, and gases. But believe it or not, there is actually a fourth state, one you might not be all that familiar with. So let's talk about it. The fourth state of matter is plasma. Now, plasma is the state of matter in which all the atoms have had their electrons stripped from them in forceful collisions. Now, believe it or not, plasma is actually the most common state of matter in the universe. But how do we know that? Well, all we have to do is look up the night sky. All those stars that you see in the night sky and our own sun, they are basically giant balls of plasma, okay? Electrons that have been, not electrons, atoms that have been stripped of their electrons, okay? And so actually what we have here on Earth are solids, liquids, and gases. These are actually quite rare in comparison to the amount of plasma that exists in the universe. Kind of humbling, isn't it, to think about that? It's massive. massive amounts of plasma all through the universe, but very little solid, liquid, and gas. We're kind of lucky if you think about it. Now, there are some interesting side effects of temperature change when objects go through changes in temperature. In fact, solids, liquids, and gases, when they increase temperature or decrease temperature, they can actually change size. This is called thermal expansion. Or rather, it's called thermal expansion when they're getting bigger. It's called thermal contraction when they decrease size. So when objects absorb heat energy, thermal energy, they actually increase in size. If they cool, they decrease in size. Now, many of you may have seen this in sidewalks. Have you ever wondered why they put those lines, those breaks in sidewalks from one chunk of cement to the next? Those are expansion joints, so that in the hot summer, as the temperature of the cement increases, those squares of cement actually expand a little. If they didn't put in those expansion joints to give them room to expand, the sidewalks would buckle up. They would crack and buckle up, just like continents pushing against each other, creating mountains. They would just buckle up and break. So they put expansion joints in to keep that from happening. Some applications of thermal expansion. Thermometers themselves. You know, we use thermometers to see how hot or cold something is. Well, thermometers themselves use thermal expansion to tell us the temperature. The liquid in the thermometer, as it warms, it expands and rises as the temperature increases. The thermometer is scaled so that as it rises, it goes through different degrees of temperature change, and we can see that. Hot air balloons, another application of thermal expansion. Hot air balloons use heated gas to expand the balloon. It fills up the balloon, and as you know, hot air is actually much less dense than the cooler air around the balloon, so the balloon is able to rise, because objects that are less dense will float in substances that are more dense. So the hot air inside the balloon rises because it is less dense. There is an exception to thermal expansion, and that would be water. Now, water actually, when you look at ice actually takes up more room than the liquid water. So when water freezes,